Hello, my name is Lisa. In this video, we'll be reviewing all of those techniques of factoring that we've talked about throughout this module. When you look at factoring a polynomial, first, factor out the greatest common factor. Then count the terms. If there are 4 terms, factor by grouping. If there are 3 terms, factor the trinomial. If there are 2 terms, check to see if the terms are a difference of 2 squares, and if so, factor the difference of 2 squares. If none of these techniques works, then the polynomial is prime. Let's do some examples. Example number 1. Again, when I have a negative coefficient, I definitely want to factor that out, but I want to look at all of my numbers here. The very first technique is to factor out the greatest common factor. 32 is -4 times 8. And I always start with the smallest number that I have and then see, are those factors of my other numbers. 48 has a factor of 4 and a factor of 8. It also has a factor of 16, and 32 could be 2 times 16. However, when I look at 40, I notice that 40 is 8 times 5. It cannot be 16 times anything. So my greatest common factor for the numbers is 8. And 48 is 6 times 8. And then I'm going to look at the variables. Remember, we always take the smallest number of variables that we have. In the middle, we have just one x and one y. The first term, we have x times x and one factor of y. In the last term, we have 1x and 2 y's. So when we factor out the greatest common factor, we're going to take out 8xy from each of our terms. If I do 8xy, 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 then I can look at what's left. -4x plus 6 minus 5y. And when I look inside parentheses, 4 and 5 have nothing in common, x and y have nothing in common. I've factored that polynomial. Example number 2, we can start the same way. Number 1, do we have a greatest common factor for all of those terms? And the answer here is yes. Each of these has a common factor of 3. So if I take out a 3, then I have 2m squared minus 6m plus 5m minus 10. Now I'm going to count the terms. I have 4 terms. So I'm going to try the method of grouping. If I group the first 2 together and the last 2 together, can I factor each group? The answer here is yes. My first group, I have a common factor of 2m, and what's left is m minus 3. My second group, I have a common factor of 5, and what's left, I'm sorry, I factored that wrong, didn't I? That's not 6m. If I take a 3 out of a 12, I have 4 left behind. 3 times -4 is -12. So when I factor now, I can take out a common factor of 2m, and what's left is m minus 2 plus 5 times m minus 2. m minus 2 is my common factor, so I have 3 times m minus 2, and what's left is 2m plus 5. So that one we could use 2 techniques on. First, greatest common factor, and second, factor by grouping. Let's look at example number 3. So, is there a greatest common factor here? And the answer is no. C squared and 21 have nothing in common. 2, we're going to count the terms. We have a trinomial with a leading coefficient of 1. So what we have to do is look at how do we factor -21 Let me write it off to the side so that the factors add up to 4. So 1 times negative 21, or negative 1 times 21. 3 times negative 7, or negative 3 times 7. And that last combination is going to do it for us, negative 3 plus 7. So when we factor our trinomial, we're going to have c minus 3 times c plus 7. And our trinomial is factored. Example number 4. Do we have a greatest common factor? And the answer here is no. 4p squared and 49 have nothing in common. I count my terms. I have a trinomial. Trinomial, leading coefficient is not 1, so we're going to multiply. Or we can factor as a trinomial using the method of grouping, or we can look to see, is it a perfect square trinomial? Is the last term positive? Yes. Is the first term a perfect square? Yes. Is the last term a perfect square? Yes. So first and last, first and last. The middle coefficient is positive, so these are both going to be pluses. Do the inside and outside terms add up to the middle term? Positive 14p and positive 14p gives us 28p. So this polynomial factors as 2p plus 7, quantity squared. Example number 5. Number 1, do I have a greatest common factor? And the answer here is yes. 18 and 32 have a common factor of 2. That leaves me with 9a squared minus 16b squared. Want to look at what's left inside. I have 2 terms. I have a binomial. If I have a binomial, I want to see, is it a difference of 2 squares? Well, is it something squared minus something squared? And the answer here is yes. 3a squared minus 4b squared, and I still have that factor of 2 out in front. So I have 2 times difference of 2 squares. We have a plus and a minus. The first thing in parentheses is 3a. The last thing in parentheses is 4b. And our binomial is completely factored. Example number 6. Do we have a greatest common factor? The answer here is no. We have a binomial. Is this a difference of 2 squares? The answer is no. It's not a difference. That tells us that this one is prime, or it is not factorable. Let's look at example 7. Number 1, do we have a greatest common factor? And the answer here is yes. Numbers that end in 5 always have a factor of 5. 125 is 5 times 25, minus 45 is 5 times 9. I have x times y, and I have x times x times x. They have in common 5, and they also have one factor of x in common. And in parentheses, what's left? 25x squared minus 9y squared. And we always want to look inside the parentheses. There's no common factors inside parentheses, but notice what we have with that resulting binomial. Do we have something squared minus something squared? And the answer here is yes. 5x squared minus 3y squared. So I still have this factor of 5x out in front. And now I'm factoring my difference of two squares as a conjugate pair. So a plus and a minus. First thing being squared is 5x. Last thing being squared is 3y. And my polynomial is completely factored. That concludes Module 13. So you should be working on the homework and the quiz for this section, and then proceed on to the post-test for Module 13. Have a great day. This is Lisa.